This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
That it would be supersonic at inlets, subsonic at inlet, supersonic at outlet, and sonic at the minimum area, the throat, and that's been called the throat ever since. And we should remember that the fundamental equation that came from the momentum equation was that rho u du was equal to minus dp. In other words, since rho is greater than naught, the pressure always falls as the velocity increases. So no matter what, the velocity is only increasing because the pressure forces, they're the only forces that are acting in the fluid. The pressure forces are accelerating the fluid. So let's just summarize the picture then. For m equal to 0 or m less than 1, then we have from the equation that I wrote that du over u is 1 minus m squared times minus dA over a. So if a is going this way, so dA is negative, then it means for m less than 1, so this is a positive quantity here, then it means that du over u is positive. And so if you have a decreasing area like that or a increasing area like that, then in this case the flow du will be positive and it'll accelerate, and here the flow will decelerate. However, for m greater than 1, just the opposite occurs. So for m greater than 1, then I have du over u is dA over a by m squared minus 1. So this is a positive quantity in the denominator here for m greater than 1. And so as the area increases, this is positive, then du over u is positive, so that's an acceleration. And the opposite would be true if a decreases, and so in supersonic flow, this would be a deceleration and this would be an acceleration. And you'll notice that in this particular case, as m goes to infinity or m gets very large, then this quantity on the left-hand side goes to 0. So for m very large, you can change the area and you're not going to change the velocity very much. Yes?
Just curiosity, so you've described the Laval nozzle, right? In practical rocket design, does it follow, are there corrections generally to the throat area, or does it very closely actually follow the mass?
I'm going to do that in a minute.
Okay.
Because in a true rocket design, you are not going to have a perfect gas, and you're going to have to use h of s and p, and a canonical equation of state. And I can tell you that I waltzed into the Moscow University, and they said, why don't we go to the sub-basement and I'll show you our lab downstairs. So I went downstairs to the lab and into somebody's office, and the lab, they had to pull on a cord to switch the light on. And we went into this office, and there on the wall I saw a Mollier diagram for liquid metal. A Mollier diagram for liquid metal. So what did I conclude? In this lab, they had to be doing shape charges, where you use an explosive to generate extreme temperatures and pressures in a metal that make it liquid, and then you use that very high temperature liquid to penetrate armor. So that is the basis of shape charges. So I knew that downstairs in this basement, and unlike a Western democracy, they don't have classified and unclassified work done in different places. So the clever people who could work these things out were in universities, and so they said, well, you can do classified research in the university. Don't talk to people about it, that's all. Well, if knowledgeable people walked in, you knew exactly what they were doing. Anyway, I digress. So now what is the maximum possible velocity you could get out of this thing? Well, the maximum possible velocity, if it were a gas, would be when the enthalpy went to zero. So you started with some stagnation or some reservoir enthalpy, H naught, and then this Bernoulli, well, it is a Bernoulli equation, this equation that we wrote down for the energy here, H plus a half U squared is a constant, would tell you that the very maximum velocity would be when H was zero, and the right-hand side would be the value where U was zero, or you'd be at the end, you'd be far upstream in the reservoir. So the maximum velocity is where it's going to be clearly the square root of 2h naught. And so for a perfect gas, you've seen me work out the equation of state for a perfect gas. P is rho RT and H is CPT. And so V maximum would be the square root of 2CP T naught. And you also saw me for a perfect gas work out what CP was, and CP minus CV was R. And and CP, and gamma is the ratio of the specific heat, CP to CV. So I could work out that CP was gamma R over gamma minus 1. So this CPT naught is 2 gamma RT naught over gamma minus 1. And I'll work it out for you later today, but the speed of sound in this particular case, in a perfect case, dp d rho at fixed s, is gamma RT naught, or gamma RT. The speed of sound is that. And so that's the square root of gamma RT. A squared is gamma RT, so CPT naught is A naught. So gamma RT naught is A naught squared, and take the square root, and so you have non-dimensionalized the maximum velocity by A naught, the upstream speed, stagnation or reservoir speed of sound, and that's equal to square root of 2 over gamma minus 1. So in air, gamma is 7 over 5. So I've got 2 in the denominator and 10 in the numerator, and which is 10 over 5. The square root of 5 times A naught is the very maximum velocity you could get out of this thing if it were a perfect gas. All right, so now I want to say just a few more things here. So U du, we know from the momentum equation, is minus dp over rho. But dp is a squared d rho for constant entropy. So this says that du over u, that'll be a u squared on the left-hand side, and then divide by the a squared. So minus m squared du over u is d rho over rho. So for small m, and this is very important, for small m, d rho over rho is much less than du over u. And that is why for very small Mach number, and the speed of sound in water is 1,500 meters a second, and so the velocity in your tap is only a couple of meters a second, and so the Mach number is extremely small. And so we don't need to worry about the change in density of water. But we would have to if we were cutting metal or fabric even with a water jet. And people today cut fabric very quickly, cut out dresses for the fashion industry incredibly quickly with water jets. Very, very high velocity water jets. So for large M, for small m, d rho over rho is extremely small, and we can neglect it, and it becomes incompressible. Whereas for large m, then d rho over rho is much greater than du over u. And near m equal 1, then we get large changes in du over u for small changes in m dot dA over A. We can see that for our basic equation. For m near 1, this is very small, so du over u will be large compared with dA over A. So for m near 1, large changes in du over u for small changes in dA over A. And m is equal to 1 only where dA over dA is identically equal to 0. Now, a quantity of interest is the mass flux rho u per unit area, rho u. So let's suppose I was interested in ddx of rho u. So what does that look like? So that's rho du dx plus u d rho dx here. And that is rho du dx, and this d rho dx I've already written down as minus rho u squared upon a squared du dx. So I can write this as this du dx, ddx of rho u is rho into 1 minus m squared du dx. So this is now arbitrary equation of state, of course. So it's telling you that at m equal to 1, this right-hand side is 0, so ddx of rho u is 0. So rho u has to be a maximum or a minimum. And we can see that for m less than 1, if it's subsonic flow, du dx, for positive du dx, for m less than 1, this is positive, and ddx of rho u will be positive, so it's here for m less than 1. But for m greater than 1, then whatever du dx is, and we've seen that that depends on the falling pressure, if the pressure falls and du dx is positive, then ddx of rho u is actually negative. So here's the maximum rho u, and yes, J is, by definition, the mass flux per unit area, rho u. The mass flux in general is rho u A, but per unit area it's rho u.
Excuse me?
Yes?
This applies also if it's minimum instead of maximum?
Yes, it would apply where if m were if the area were a minimum, so m is not equal to 1, supposing it's subsonic, then the right-hand side is positive, and so ddx of rho u is of the same sign as du dx. So u would be increasing through there. Could be, or du dx would be 0 if it's not a sonic throat. If it's not a sonic throat, du dx would be 0. All right. Now, I want to do just a couple more things, qualitative things, so that you actually get a feeling for what's going on here, rather than just solving equations, that you actually get some real physical insight into what on earth is happening here. So, what that leads us to do is to say, well, look, there's a reference condition here where the rho u is a maximum and it's at A star, where that's a sonic throat condition. So, for example, here is A over A star. So for A over A star increasing, so if we say where A is A star is 1, then we can get Mach number less than 1. We can come down here as we approach this thing, and then go back up again. Or if we keep dropping the pressure, we could come down to here at 1, and then we would be supersonic beyond that, and the pressure would continue to fall as the area increased, and that would be supersonic flow. And if you plot here P over P naught, so we start here at some infinite area far upstream, where the pressure is the reservoir pressure P naught, and that's equal to 1, so we're here. Now as the pressure falls, it can fall way, way down here. And as it falls, the Mach number can increase like this. And this is u over A naught. And the very maximum velocity would be right out here where the pressure's gone to 0 and the temperature's gone to 0, and we get the maximum velocity way out here. So that's u over A naught, gamma minus 1 over 2, and this quantity goes to 1 when we have a maximum velocity. U maximum over A naught is the square root of 2 over gamma minus 1. And we just plotted rho u over rho star A star, and its maximum value is right here, and it has a curve that looks like that. For the pressure. So the reference conditions are the starred conditions, and they are where the conditions where the flow reaches sonic velocity and m is equal to 1. And this is the only point where A is well defined in an accelerating flow. Not upstream at the reservoir conditions, or downstream. You don't have a reference point downstream where u's going to a maximum, where rho's going to 0, and again, A is going to infinity. So far upstream, A is going to infinity. Far downstream, A is going to infinity. And there's only one point where you have a reference condition, and that's A star. So the sonic conditions are very important, and you'll see plots of A over A star and so on in a minute. So let's work out some things here. So let's work out some results for a perfect gas. Firstly, even if it were a not perfect gas, we are going to be constrained by the energy equation, which is h plus a half u squared is h star plus a half A star squared is equal to h naught. So for a perfect gas, we can write that h is equal to CPT. Now, why so you saw that it was CPT, and that CP was gamma R over gamma minus 1, which I proved to you earlier, that CP minus CV was R. And by definition, and then I'm wanting to say that gamma RT is A squared. Well, now, why do I say that? Because before, you'll remember that I worked out for an arbitrary fluid that if gamma was the ratio of the specific heats, then P was some constant rho to the gamma e to the S over CV. So dp d rho at S equal to a constant. Let's take dp d rho of this. I'll get K gamma rho to the gamma minus 1 e to the S upon CV at the same S. S is a constant. Well, this K rho to the gamma is P. E to the S on CV is P. So this was gamma P over rho is what this expression is here. Gamma P over rho. So dp d rho at fixed S is by definition A squared. So A squared in this perfect gas is gamma P over rho. But P over rho is RT. P is rho RT in this perfect gas, so this is gamma RT, and that's A squared. So A squared is gamma RT. So you will need to know that. So CP is gamma RT over gamma minus 1, so that's A squared over gamma minus 1. So I can replace H by A squared over gamma minus 1. So I have H plus a half U squared, or A squared over gamma minus 1 plus a half U squared is equal to A star squared over gamma minus 1 plus a half A star squared, because at the throat, U is equal to A star. And that's equal to A naught squared over gamma minus 1 far upstream where the velocity is negligible. So we can see that we have an expression here for A star squared in terms of A naught squared. And A star squared, just put the denominator here as 2 into gamma minus 1. And I have 1 plus, 2 plus gamma minus 1 is gamma plus 1 over 2. So that's gamma plus 1 over 2 into gamma minus 1. The left-hand side is times A star squared. So I have an expression here automatically for A star squared over A naught squared. And we know that that's T star over T naught, and that's equal to 2 over gamma minus 1. 2 over gamma plus 1. Because you just look at this and you can cancel the gamma minus 1 down here. And I've got A star squared over A naught squared is 2 over gamma plus 1. So I have an expression for the ratio of the temperature to the stagnation or the reservoir temperature. And for gamma equal to 1.4, T star over T naught. T star over T naught is 5/6, and you can see that. Just put Sempron over 5 in here. So I've got 12 here and 10 on the top. So that when I take, oh, wait a minute. Yes, 10 over 12 is 5 over 6. So, and for gamma 5/3, which is the other typical case, monatomic gas, T star over T naught is 3/4. And we also see very quickly that I've got A naught squared, and I've got here, if I divide by A squared, I have 1 plus gamma minus 1, or if I multiply this gamma minus 1 throughout, I'll have 1 plus gamma minus 1 over 2 u squared over a squared is m squared, and that's equal to a naught squared. So a naught squared divided by a squared, if I pull the a squared out of this and I have an m squared in there, it'll be t naught over t, which is 1 plus gamma minus 1 over 2 m squared. And so that will also hold for steady channel flow of a perfect gas if, if it's also isentropic. If it's also isentropic, then we have that S minus S naught over CV is the log of P over rho to the gamma by rho naught over P naught to the gamma. P over rho to the gamma is a constant. And P is rho RT, so this means that T over rho to the gamma minus 1 is a constant. And that says that T, so if I put P as rho RT here, T is like T over rho to the gamma minus 1 is a constant, or T's going like rho to the gamma minus 1. And so rho goes like T to the 1 upon gamma minus 1. And now if rho is going like this power of T, then P is going like rho to the gamma, so I got to multiply this T to the 1 upon gamma minus 1 to the gamma. So P is going like T to the gamma over gamma minus 1 times a constant. So that tells me immediately that if I know what T naught over T is, then for this isentropic case, so this is isentropic, S is equal to S naught, for example, then I get these results. And so if I know what T over T naught is, it's going to tell me what that I'll have rho naught over rho and P naught over P will depend on T in this way. So P naught over P will go like T naught over T, 1 plus gamma minus 1 over 2 m squared, raised to the gamma over gamma minus 1. And rho naught over rho will go like T naught over T to the 1 over 1 gamma minus 1. So it's 1 plus gamma minus 1 over 2 m squared. Now that's the sort of thing that you'll see endless charts of in any book on compressible gas dynamics, where they make assumptions that it's a perfect gas. Okay. So just let's look at this. So here's P naught over P. Well, we can get that in numerous ways, but if we put m equal to 1, so this becomes P naught over P star. If for m equal to 1, it's 1 plus gamma minus 1 over 2. So that's 2 plus gamma minus 1 is gamma plus 1 over 2. So it's equal to gamma plus 1 over 2 raised to the gamma over gamma minus 1 is P naught over P star. And rho naught over rho star will be gamma plus 1 over 2 to the 1 over gamma minus 1. And you should have these numbers in your back of your mind, that P star over P naught will be 2 over gamma plus 1, and gamma plus 1, if gamma is 1.4, that's 2.4. 2 over 2.4 raised to this power, and the answer is 0.528, so it's only just above a half for the ratio of the pressure to P naught at gamma, for gamma equal 1.4. Rho star over rho naught, the density also falls when you go through the throat, and the density falls to 0.634 for gamma is equal to 1.4. All right. So there's another important result which follows from all of this, and that's, let's look at the mass flux, which we've said is constant for this one-dimensional flow. And the mass flux is rho AU, and that's rho star A star A star, and that's constant m dot. So m dot could be written in another way. It's rho star over rho naught times A star over A naught multiplied by rho naught A naught by A star. So that's the same expression as this. And this rho star over rho naught and A star over A naught are functions of gamma. We've just done that. Rho star over rho naught and A star over A naught. Well, A star over A naught I think I had just up here. Yes, I did. A star over A naught was the square root of 2 over gamma plus 1. So I can, this rho star over rho naught is a function of gamma, and A star over A naught is a function of gamma, and I'll keep this part here. So I've called this thing here capital gamma of lowercase gamma, rho naught A star. And if you work out what capital gamma is, it's this rho star over rho naught, which we had, which was 1 upon gamma minus 1 and 2 over gamma plus 1. And this was a half of this, because it's the square root of the T star over T naught, and you add the two together and you get, it's 2 over gamma plus 1. So now you can do this, and you got 2 plus gamma minus 1 is gamma plus 1 over 2 into gamma minus 1. So this is this elaborate function of gamma, ratio of the specific heats. And that ratio is 0.5787 for gamma 1.4, and it's 3/4 squared for gamma 5/3. That's interesting and important because it tells us that I can write rho AU is rho star A naught, which is m dot. So it's telling you that rho AU is m dot, and that's gamma of gamma, rho naught A star. So rho AU. So let's divide A by A star. A over A star is gamma of gamma, rho naught A naught divided by rho U. And if I divide this by A and multiply it by A in the denominator, I get 1 upon a Mach number, and I get a rho naught over rho, and I get an A naught over A. And so A over A star is this capital gamma of lowercase gamma, 1 upon Mach number, and I've got these quantities, rho naught over rho and A naught over rho, and they're 1 plus gamma minus 1 over 2 m squared to the, this is the rho naught over rho, to the 1 over gamma minus 1, and this is the T naught over T to the 1/2, and that's plus 1/2. So this is sometimes written as just an elaborate function of gamma and Mach number. And that equation for A over A star is equation 5.2 in Modern Developments in Gas Dynamics, Liebman and Roshko. Equation 5.2. And A star is therefore a reference area, and that may or may not exist in the flow. There may be no A star, but I can still use it. And it requires, for it to exist, requires sonic velocity.
So that's still the throat, right?
That's the throat.
Yeah.
But there may be no throat.
Yeah.
It may be entirely subsonic. So I want to illustrate that. So here is A over A star, and here's Mach number. And here is where A over A star is equal to 1 and M is equal to 1. So that's 3 right here. And this behavior is for A over A star behaves this way. You approach sonic velocity, you come down here, A is getting less as the Mach number is increasing. So if I had a nozzle like that, which is entirely subsonic, I'd have M less than 1 here, and I'd be at condition 1. And then I'd increase the velocity, and the Mach number would go, would increase, but it's still less than 1, and I'd be at 2 here. And so it's still less than 1. And now I have this increase in area, and the Mach number goes down again. So I come from 1 to 2, and I go back to 1. This particular case is where I'm here at 1, I'm here at 2, and then 3 is the minimum area here. And now, if the pressure falls, I get supersonic flow, and I come back up this branch. A over A star is increasing, and I come back up here to 4, but now I have M greater than 1. That's a very important plot. That is the heart of a supersonic rocket nozzle. And now you tell me why these nozzles aren't infinitely long. They're not infinitely long because the momentum flux that you get out of this thing is starting to fall. And that's because even though the velocity increases, you can't go beyond the maximum velocity. And if you have a constant mass flux, the momentum flux out depends on the mass times the velocity. So there's no point in making the area go to infinity, because even though the velocity is not changing very much. So the momentum flux that you're getting out is not that much. And so you don't make the rocket nozzle infinitely long. And because you'd carry all that extra weight and you wouldn't get much benefit in terms of the momentum flux out, even in vacuum. So, what actually determines the flow? So this figure is critical. And I guess I'm going to have to leave it somewhere here soon for today. So what determines the flow? The heart of the matter, of course, is the pressure difference. So let's suppose that we were on that 1, 2, 1 branch. We came down here, we came to the throat, but we still had Mach number less than 1, and then we recovered the pressure. And we haven't quite recovered all of the reservoir pressure because we've still got some velocity. The dynamic pressure has not all gone to 0, and we haven't fully recovered the pressure that we had far upstream. Now, supposing the pressure falls and we went through the throat at Mach number just slightly less than 1. Just slightly less than 1. Now, as the pressure increases, as the area increases, the velocity decreases, and we come back here on this subsonic branch. So we are in terms of this figure here, we've come down here. We're not quite sonic. We're just here. And then we come back up again, and the area increases, and we come back up to 1. So that's a branch point, if you like, where something radically happens. If I drop the pressure, I've now got to drop it a long way. And that's fine if I'm actually got a rocket nozzle in vacuum, then the pressure outside is extremely low. And we'll figure out how to work that problem out. So, if the pressure keeps falling, and this is the pressure, P naught over P star, or P star over P naught here, here's 1 up here, P star over P naught, we worked out was 0.528 for gamma, I think that's what it was, 5.528, I think so. So it's just a little bit more than half of the stagnation pressure. So I got to drop the pressure. So if I started at 20 atmospheres or 100 atmospheres, then I'd be at sonic conditions when the pressure was a half of that, roughly speaking. 100 atmospheres, I'd be at 50 atmospheres in the throat, roughly speaking, 52. Just a little bit more than a half. And now if I keep dropping the pressure here, then I'm on the supersonic branch, and I'm headed towards, I've gone through the throat, I came down to here, and now I'm headed up to 4. And Mach number is greater than 1. And so a critical question is, what's the solution if the downstream pressure is not this value and not this value? What would happen? And we have to talk about shock waves in order to make that real. What actually happens? So we will complete the discussion after we've talked about shock waves, because what will happen is that you have supersonic flow here. A shock wave takes you from supersonic flow to subsonic flow in a discontinuity. And we'll see whether you can have a discontinuity and whether a shock wave is possible. We'll see that not next week, but the week after. So we have to put a shock wave in, and there'll be a shock wave, and it'll take us to subsonic flow, and then we'll be on this branch like this one here.
Yeah,
So
this is always a source of confusion for me. So as you're going down, or as the nozzle is expanding,
right,
and the Mach number is increasing, I feel like that determines the pressure, right?
it does.
So physically, what would cause the pressure to not be the required pressure for that Mach number and for a shock to occur?
Well, no, it will occur, but the shock wave takes you from supersonic flow to subsonic flow.
Okay.
But the subsonic flow will feel the downstream condition all the way up. And that drives a wave which becomes a shock wave. And so the subsonic branch exists from the shock wave downstream.
So the pressure is following the pressure.
So it follows this exactly,
And it goes straight up.
and then it goes straight up, and then it'll go up like that.
And physically, what causes that?
What causes it is that the downstream pressure is felt
Oh, okay.
because it's a subsonic flow.
Yeah.
So the speed at which any disturbance from downstream is felt propagates upstream at the speed of sound. And so if it's subsonic, it can feel that downstream boundary condition. So it's not complicated, but you have to think. And I love Oppenheimer's remark, we learn, you learn, by explaining what you don't understand. We learn by explaining to each other what we don't understand. That is so important. If you're not doing that, you're wasting your time at this university. If you're not explaining to the guy who's trying to teach you something what you don't understand, you're missing the point, honestly. And I think some of you are too timid. You don't speak up. For God's sake, speak up. Okay, so this tells us something. What if the situation were like this? So we cut this nozzle off, so here's the end of the rocket nozzle. And then we have some great big reservoir out here. And it could be the Earth's atmosphere. We could be on Earth. And that pressure is about 1 atmosphere. Well, we do know that this pressure, if this process beyond here is not isentropic. We do know that this reservoir pressure, by the time this flow has practically zero velocity, this reservoir pressure is much, much less than this pressure here. You threw away, the entropy had to increase. And so you threw away you had isentropic behavior up to here, but then you didn't. You didn't. And it has to mix, and there's lots of current, and there's lots of thermal currents, and there's lots of viscous currents, and so you're losing all that entropy. Okay, you're gaining entropy. I mean, you're losing all that that total pressure. So now, well, I got to quit, but I'll quit with this.
Oh, yeah, you're right.
I'm nearly about to quit. Supposing we're talking about a gas and we're looking at the lunar lander and we're wanting to design a rocket nozzle, an engine, to operate behind the moon. Okay, so the guys who did this were your age. And they weren't mechanical engineers. They weren't aerospace engineers. They were mathematicians. They were at TRW. How did they do it? Well, and what did they do? Why did they have to fire the rocket nozzle, fire the engine behind the moon? And why would that be difficult? Well, the first reason why it's difficult is that you can't communicate behind the moon. You couldn't send radio waves from somewhere, some radio telescope somewhere, or some transmitter somewhere, some aerial somewhere. You couldn't send them to behind the moon because they couldn't receive it. So you had to make an extremely accurate engine. So now, we'll come to how they did it in a minute, but firstly, why did they have to have an engine? And which way would it point? So here's the moon, here's Earth, and these guys are over here like this. What would happen if you didn't have an engine? Beg your pardon? You'd go around the moon, and then what would happen? You'd come back to Earth. You'd come all the way back here. So you had to lose a lot of energy, right? What if you lost too much? Crash where? In the moon. You'd come in here. So you better get it right. And you can't talk to anybody. So you're the guys in charge. How are you going to do it? How are you going to do it? Well, I'll tell you how they did it. Very clever idea. They considered 2 hypergolic fluids, liquids. What's a hypergolic liquid? A hypergolic liquid is 2 hypergolic liquids are liquids which burn on contact. On contact, they burn to a very high temperature, producing a gas. So that sounds like a good idea. I'm going to produce a gas, probably a relatively low speed of sound. I can get supersonic nozzle through this rocket nozzle. Okay, now, what is going to be terribly important to get the right control over this engine? What is going to be terribly important? Not only the upstream temperature. The upstream temperature will be determined by the combustion of these hypergolic fluids. So that will determine the temperature. What will also be determined? If you have a sonic throat, you'll have a mass flux. And the mass flux will depend on the upstream density and speed of sound, as we've just seen, or as I'm about to tell you. So that what becomes important is you want to be able to control the pressure extremely accurately, and you want to control the stoichiometry extremely accurately. So you always get the same temperature. How are you going to control the stoichiometry of these two liquids? You're going to store them separately, right? How are you going to control the stoichiometry? You're going to make a ganged valve that produces a sheet So you produce out of here a sheet of fluid, and you put it through a whole bunch of holes upstream here so that you can control how fast it's moving and how large the flow rate is. But I want the exact stoichiometry. 1 mole of this and 1 mole of that, for example, exactly. How am I going to do it? I'm going to make a ganged valve that as I open up these holes, I'm going to open up exactly the same number of holes for the other fluid. And I'm going to make sure that they mix by putting my holes on a spiral around here. And so one of them's coming out like this. It's going to make contact because they're in perpendicular directions. They're going to make contact, and they're going to burn, and they're going to be stoichiometric. If I bring exactly the same flow rate here as I have here. So I need a gang valve. So it was a gang valve which opened up those volumes exactly. And it burnt. And so they were controlling the temperature extremely accurately, and they controlled the pressure or the mass flux very accurately. The mass flux was obviously dependent upon this valve. The valve controlled the mass flux. And so you had a throat, and you had a mass flux, and so you controlled the rho star and A star through there. A star is determined by the temperature. So, but you were controlling the pressure. So that's how it worked. All right. Well, next time I got to quit, I think. But so this is if you had a non-perfect gas, exactly like this case, what would you need to know? Beg your pardon?
The state.
The state, right. You need to know an equation of state. What's a canonical equation of state from which you can get everything? All of the thermodynamic variables. There are 4 of them, and I talked about it, and that's why I spent as much time talking about it as I did, because you're wasting your time if you think that all of this is about playing around with algebra and working out perfect gases, because the real problem ain't a perfect gas. The real problem is that I'm given some equation of state, H of S and P. And that's the Mollier diagram. H of S and P is a Mollier diagram. And I also need to know the thermodynamic identity. What's the thermodynamic identity? It comes from what thermodynamic law? Good God. The first law.